Next, we're going to go to field data tables. Our field data tables are what we're going to use to ultimately create our final firing solution. These are loaded with data, and at first they're intimidating. When you look at them, you're like, wow, that's a lot of numbers, and it can feel real intimidating. But let's just go over them real quick so you know the information is on here. At the top, you have your overview information. This is the same information that you submitted for your original set of cards. Now, you can go back and resubmit this information so you can get updated cards as things change, as you true out your BC, true out your velocity. You can make those changes as needed. And they're unlimited because we have an automated system now set up. So this is a huge advantage to those that have been supporters of the 1stShot project. Moving down from there, we have just a standard mill reading for a 6-foot target. This goes across the top of all the cards. This is just where you can go to make a rapid calculation if needed. We then have our 1 mile an hour. This is for a 1 mile an hour moving target. So if you have a 100-yard range at 1 mile an hour, you know, with this particular load, you need to give it about 0.6 mil lead. As you move out to 700 yards, it turns into a 0.7 mil lead. It also gives you your Coriolis, spin drift, your time of flight, and your energy on target at range. Moving down the left-hand side of the card, this is your density altitude that you're operating at. So I know it looks weird to have negative 3,000, negative 2,000, negative 1,000, but it's actually quite possible. If you get cold temperatures at a low altitude, you will very easily get to a negative 1,000, negative 2,000 feet density altitude. It's also very easy to get up to 10, 11,000 feet density altitude if it's a hot day at a mile high. So you can definitely get up to 8,000. And as you move across here, you'll see the range goes across horizontally, and your density altitude goes vertical. So whenever you need to pull together your range or density altitude, then you just go to the range you need, drop down to the density altitude that you are at, and pull it up. So let's look at, we've been talking about a 6-foot target that was 2 mils. We calculated that was 1,000 yards on the table. You see how quickly that happens on this chart. And then from at 1,000 yards, we calculated that we were at 3,000 foot density altitude, which gives us an initial 7.6 calculation, 7.6 mils in this case calculation. But that's how quickly you can pull it up. You know, for a 1,000-yard shot, you'd need to calculate out a little more precise. 700 and under shots, you know, you obviously can begin to make those determinations depending on the range you're at and the accuracy level that you need. But this is all the information that's on each of these field data tables. We run them from 100 yards all the way out to 1,400 yards. Obviously, making a 1,400-yard shot without a ballistics computer is pretty impressive. And I've calculated these out, and I've been able to get within 1/10 of a mil of what a ballistic calculator can do. At 1,400 yards, it's still, I mean, that's an amazing shot. So let's move on to building up the firing solution from that data table. For every single shot you build, you can build it inside the system. Make sure you don't miss a step. Now, for rapid engagements, you're going to have your own system set up. This is for making sure that that one shot you have, you've covered every variable that you can quickly account for without a ballistics computer to make sure that you are going to hit that target on your first shot. This entire system was designed around first shot engagement, not a shooting and then doing a correction. This is all designed for really a cold bore performance. So we determined earlier that with density altitude, we were looking at 28 inches mercury, 70 degrees, 3,000 feet. So what we'll do is we will put that into our firing solution right here on the engagement data card. So density altitude, 3,000 feet. Then We ranged 72-inch target, 2 mils, 1,000 yards. We'll put that in our variables here, 1,000 yards. We're able to look at our chart for our field data table here, and it's 1,000 yards, 3,000 feet density altitude, 7.6 mils is our initial. That's our initial correction. Now we're going to make a correction for ammo temp. Our ammo's been sitting in the sun. It's 80 degrees, and because our ammo is warm, it's actually going to increase our muzzle velocity, and it's going to slightly decrease the correction that we need to input. So we're going to actually lower our point of impact, so that way we can compensate for that higher muzzle velocity. Now this calculation is going to be pretty accurate. We've looked at a lot of different powders. Most people are running 4350, and that's what this calculation is run off of. So I would trust it until you're getting data that shows that it's not reliable for you, but it's going to be really close. So we're going to put in 80 degrees for our ammo temp, which was negative 0.8 for our mils at 1,000 yards. That pulls us down to 7.52 mils for our correction. We're going to assume that this is a 20-degree angle of fire shot, which is a 94% value. So angle of fire, 20 degrees, 94% is the cosine. That brings us down to 7.07 mils for our correction. Now we're going to look at Coriolis, 1,000 yards. We're going to go to our Coriolis, 0.08 mil correction on that. And because we're shooting to the east, where it's going to be a negative. If you're shooting to the west, it's going to be a positive. So that brings us a final firing solution of 6.99, so that's 7 mils. So we're going to dial 7 mils. You can see how this changed out, because originally we would have dialed 7.6 if you were just running off of your density altitude. But each of these things had a slight impact on our overall result, which ended up being 0.6 mils. Makes a huge difference at 1,000 yards. Alright, so now we're going to look at wind. 1,000 yards, 3,000 feet density altitude. Here is our correction for every 1 mile an hour of wind. Now this is a full value correction. So for every 1 mile an hour wind, we have this full value correction. So 0.18 at 10 miles an hour. This is just an arbitrary number that I put in. Obviously you'd have your own wind measurement. So your wind speed measurement would be that. So 10 mile an hour at 0.18 is 1.8 mil wind correction. Now we have to look at what is the angle at which the wind is attacking our firing position. So if our rifle muzzle is this direction and the wind is coming in, it looks like at about at 11 o'clock, but we always use the cosine because it's more accurate. 34% is going to be our calculation on that, which brings our correction down to 0.61. From 1.8 down to 0.61. Now we're going to look at our spin drift. We're going to correct to the left because we have a right twist in our barrel. 1,000 yards. Correct to the left, 0.22. We're going to put that in for spin. 0.21. Sorry, missed it by a thousandth there, or a hundredth. And so that brings us to 0.4 correction. With that 0.4 correction, we're going to look at Coriolis again. This Coriolis is going to be for your wind, so this is on your vertical. This is going to be on your wind correction. 0.08 mils at 1,000. So we're going to put that in. Your final firing solution is 0.32. So 0.3 mils is your original. When originally you could have calculated this out if you didn't have an accurate wind angle reading and you didn't put in your spin or your Coriolis, you can see how big of a difference that makes to not have each of these. Now with the ballistics computer, a lot of times they do all this for you, but you'd be surprised how fast. I can actually run this faster than a ballistics computer if you have to literally get your phone out of your pocket and go through and put everything in and adjust everything. I can get through this as fast as you can get through that. So we're going to also do a quick calculation for a mover at 1,000 yards, 0.77 per 1 mile an hour that this mover is going. We know that this is a 3 mile an hour target. So 0.77 times 3 is a 2.31 hold. And now you know that you can dial for your wind if you want, and then hold for your target. Or you can add these two together and hold for 2.6 and hold for all of your correction on your windage. So in this case, you would dial 7 on your elevation, hold 2.6, or dial 0.3 and hold 2.3 on your target. And that's going to be how we ultimately build the firing solution with this system. What's nice about the engagement data card is it literally walks you through every single step, helps you visualize what you're actually putting together for your firing solution, and really makes you conscious of what's going on. It's very easy inside of a ballistics computer. Just put in your data, boom, done. You don't even think about what is going into and what is going to affect that bullet on its way to its target. I think that this really helps us get a good understanding mechanically from an external ballistic standpoint what's going on, and to have this in your bag is going to be priceless at some point, I think. So be sure to appreciate everyone's support here at 1stShot, and if you guys have any questions at all, just email us, info@1stshot.org or pfs@1stshot.org. PFS is for Precision Firing Solution, and you guys want to just test this out and check it out. We want feedback, and we're making it better and better every single day. So we do appreciate it, and if you have any questions, we look forward to responding to your emails. Take care.